Good morning, everyone. I'm Biaoshuai. This is a joint work with Schoenebeck is also here today. And the topic is just inference maximization on undirected graph towards closing 1-1 OE gap. And by the way, I'm a fourth-year PhD student, and I will be on the job market very, very soon. So Cascade in the social network is everywhere around the world. There are some typical examples like the spread of the virus and the viral marketings. And in these two examples, it's about the spread of the use of the buzzwords across the internet until a certain buzzword becomes popular. And in general, the Cascades process like this, you have a graph which models the social networks, and you have some initially infected vertices, which are called the initial seeds. And then these seeds try to infect their neighbors. And it goes iteration after iterations. And the infection might be successful or maybe not, depending on the cascade model you use. Also, if a vertex is infected, it will stay infected throughout the entire process. And at the end of the cascade ends when there's a new iteration, there's no more infected vertices. And talking about inference maximization, one canonical example is the viral marketings. So viral marketing is a marketing technique that a certain company advertiser want to promote the brand awareness through the word of mouth effect. And it can be viewed as an optimization problem. You are given a fixed budget K, that enable you to give the product to K people for free. And the question to you is that given you are presented the graph, the network, how to choose the K seeds properly such that the total number of influence is maximized. And more formally, inference maximization problem is an optimization problem where you are given these three inputs. You are given input graph G, which may or may not be age-weighted, depending on the cascade model you are using. Of course, you are given the cascade model. In general, locally, cascade model describe how each vertex is infected by their neighbors. And globally, this induces what we call a global inference function sigma, which maps a set of vertices corresponding to the seeds and output a real value, which is the expected total number of infection at the end. Notice that I say this is an expected number because most of the cascade model are stochastic. And we are given a fixed budget, which is a positive integer k. And as an output, we output a seed set S that has size at the most k that maximizes the expected total number of infected vertices. Any questions so far? Great. In a seminar paper in 2003 by Kempe, Kleinberg, and Tados, there were two cascade models that has been introduced. The first one is the independent cascade model. I think you have already seen this in the previous talk. And it says that for each edge UV, each infected vertex U, say U is already infected, it has only one attempt to infect V with probability PUV. And this can be viewed as the weight of the edges if you are given a weighted graph. And these probabilities are independent. And that's why the model is, say, independent cascade model. And there are some two well-studied special cases. The first one is called the uniform independent cascade model. This basically says that we have the same single P for all the edges. And the other well-studied special case called the weighted independent cascade model. And now we don't want to have the uniform weight of the edges. Instead, we want the weight of PUV to be 1 over the degree of V. This model the scenario where a high degree node are less likely to be infected by a single infected neighbor. And another well-studied model is the linear threshold model. So the idea of linear threshold model suggests that the inference from these different neighbors should be additive. And to model this formally, before the cascade process begins, we have each vertex sample a threshold theta V independently and uniformly at random from 0 to 1. This threshold measures the vulnerability this vertex is against the infections. And on the other hand, we try to calculate the total amount of influence that we suffered from the neighbors. So we for each this infected neighbor U, we sum up all the weight of the incoming edges that connect the infected neighbor U to the vertex V. So the left-hand side of this inequality is the total amount of inference that we suffer from the neighbor. And if this is greater than the threshold, we will be infected. And there's a standard assumption which keeps the whole thing linear, saying that if you sum up all the incoming weight of all the incoming edges, it should be at most 1. And there's also a special case, which is like the most common case in the at least in the practical work, called the uniform linear threshold model. It's like the weighted independent cascade model. We assume the weight is 1 over the degree, which again model the scenario that the high degree vertices are less likely to be infected by the same amount of infected neighbors. Any question before I move on? Great. In this work, we will focus on inference maximization with undirected graphs. And the reason we do that is, firstly, in our real life, many networks are undirected by their natures. For example, like friendship and like a co-authorship, they are all undirected. Also, undirected network has been like widely considered in the empirical work as well. So it's been considered in most, but if not all of the empirical works. And in these 4 works, we realize that they exclusively consider undirected graphs. So when we try to adapt the linear threshold model and the independent cascade model to the undirected case, the adaptation is kind of very in a natural way. So firstly, each edge is bidirected, represented as 2 antiparallel edges. And all these models are just extend to the undirected case in their natural ways. And there's one thing I need to point out is that people don't normally consider like the general linear threshold model for undirected graph. So that's why I put a dash here. So if we are doing undirected graph for linear threshold model, we automatically assume that we are doing uniform linear threshold model, such that the weight is 1 over the degree. So in this slide, I'm going to briefly mention the most relevant existing results. So firstly, as most of you may probably already know, that in the seminar paper, they show that the greedy algorithm that iteratively selects the seed with the most highest marginal increment on the objective function achieves 1 minus 1 over E approximation. This is basically because that the objective function under the under the independent cascade and linear threshold models is submodular and monotone. And with doing greedy always ensure 1 minus 1 over E approximation. And for the hardness result, it's been known that linear threshold inference maximization is NP-hard, and this holds even for undirected graphs. And for the independent cascade model, there's a lower bound hardness result match the approximation ratio. It's NP-hard to approximate within 1 minus 1 over E plus epsilon for any constant epsilon, which are greater than 0. However, this result only holds for directed graph. And if we are talking about undirected graph, we do not even know if the problem is NP-hard, where I put a star here because there's indeed an APX-hardness result, which I'm going to talk about in the next slide. So perhaps most relevant to our work is Khanna and Lucier's work in 2014. They show that they work on the problem with independent cascade model on the undirected graphs. They show that if we are doing undirected graph by taking advantage of the undirected nature of the networks, the greedy algorithm actually achieves slightly better than 1 minus 1 over E approximation. Also in the same paper, there's an APX-hardness result on a more general model. In this more general model, we have the seed, we have a prescribed subset of the vertices that are given as input, where the seed can only be chosen in this prescribed subset. So this is a more general setting. Any questions so far? So this table summarizes what I've talked about in the previous few slides. So on the positive side, on the approximation algorithm, the greedy algorithm can do 1 minus 1 over E approximation for all of them. So the first table is about the independent cascade model, and the second paper is about the linear threshold model. And we know that for the undirected case, we can do slightly better due to Khanna and Lucier. And on the hardness side, there's much to do. So we only know that for the directed case independent cascade model, the gap is closed, and it is unknown for the remaining, for the undirected model. And as I mentioned, for the linear threshold model, we do not know any hardness of approximation result. We know the exact optimization problem is NP-hard. So our main contribution is to provide the APX hardness result for all these settings. So which we show that there is a constant tau such that approximation the optimal sigma within a factor of 1 minus tau is NP-hard. So this is an improvement of these previous results. Any questions? So here in the remaining part of the talk, I'm going to sketch like the technique of the proof. So we reduce the problem from Dinur's PCP theorem, which says that max 3 set is hard to approximate, even if we assume that each variable only appears in constant number of clauses. And another piece of our proof is to provide the upper bound to the sigma s for undirected graphs. And this upper bound, we believe, are interested on their own. We show that the total expected number of infected vertices is upper bounded by the size of the seed plus the edge cut, meaning that the number of edges between the seed sets and the non-seed sets. So this holds for the weighted independent cascade model and the linear threshold model. And we believe this is an important observation because this says that although the cascade is a global process that happens for more than one iterations, but still the total number of infections is going to be upper bounded by some local characteristics. So we only look at the S and their neighbors, it provides an upper bound to sigma S. In particular, even if the remaining part of the graph is kind of well connected, that is very helpful to the cascade. As long as S is weakly connected to the remaining part of the graph, the total number of infections would be limited. And this observation holds for weighted independent cascade model and the linear threshold model. For the uniform independent cascade model, this definitely doesn't hold because we can have P equals to 1 for all the edges, so we cannot bound the sigma S locally. But still, we have this bound, which is less clean, and it depends on, rely on the independent cascade parameter P and the maximum degree D, and sometimes doesn't work in the case that the denominator is not positive. But still, this bound is useful to show the APX hardness results. And I would like to emphasize that all these bounds only hold for undirected graphs. None of them works for the directed graph. For a single counter example, you can have a directed line pointing from a source to a sink, and in all these models, all the edges are 1, has weight 1. So if the source is chosen as a seed, all the vertices in the line will be infected. So these all bound will fail in this special case. And I'm going to first talk about how to prove this upper bound by a sketch. And secondly, I'm going to in very high level talk about the reduction from max 3 set. And notice that the upper bound in the first part will be used to prove the soundness of the reduction. And firstly, I'd like to prove a lemma for the linear threshold model and the weighted independent cascade model. If G is an undirected forest with S being the roots, then sigma S is exactly this upper bound. So the proof is simple. Recall that the weight of the edge is 1 over the degree. So consider this part of the graph where we have 3 leaves and 1 internal node. And suppose the vertex outside connecting to this guy is already infected. So the expected number of infected vertices in this region is 1, because we have 1/4 chance this guy infected, and then this guy has degree 4. And once this guy is infected, all the 3 leaves will be infected. So the expectation is 1. And this suggests that we can just contract the host into a single point, and the expectations remain unchanged. And we can keep doing this until we have instead of forest, we have a collection of multiple stars, and this upper bounds become very apparent. And to prove this in general, the idea is that to try to find a larger graph, G hat, which we call is a forest, and which preserve the size of the edge cut, also, and meanwhile ensure that the number of infections, expected number of infections, weakly more than that in the original graph. And basically, this looks like a BFS search tree, but each vertex can be reused. And a coupling argument, this is like a very high level. We can show this by a coupling argument by corresponding the same probability event from the old graph to the new graph, showing that whenever we have a few fixed number of vertices infected here, we have the same or even more infected vertices in the new graph. So this coupling argument can show this upper bound. And if we put in together, we can show that this upper bound holds in general. And part 2, I'm going to show this in a very high level. So as a corollary to Dinur's PCP theorem, we know that the maximum independent set is APX-hard. This even holds for the D-regular graphs with constant D. And the reduction is the same. Think about the inference maximization graph is the same as the independent is the same as the independent set instance, and we are choosing the size of the seeds, number of seeds the same as the size of independent set. If the graph has a k independent set, in this case 5 independent set, we choose them as the seeds, then the total number of outgrowing edges is going to be k times d, and all these edges will be useful to the infections. And in the no case, we know there are constant, for any k vertices, there are constant fraction of edges that are internal, which helps nothing at all to the cascade. And by applying the upper bound for the first part, we can show that the no instance, the total number of infection is kind of a constant factor reduced compared to the yes case. And this roughly intuitively shows the APX hardness. And I'm going to briefly talk about our second part of the result. So the motivation is that this upper bound holds in general, but this upper is tight when the graph is a sparse or when the graph is a forest. So our guess is that in a real social network, the graphs are normally sparse. So this upper bound may also be like a good approximation to the sigma. So instead of doing original greedy, where we compute the sigma function by the Monte Carlo sampling, which is very expensive, we trade the seed quality with the scalability by just doing greedy on the approximation version of sigma, where we approximate sigma by just a local objectives. And this is the result we have for the linear threshold model. So the first blue line is the greedy algorithm. You can see our heuristic is the red line. We can see our algorithm is very close, almost identical with the blue lines. And our heuristic also outperform other popular, other successful local greedy heuristic, like we compare our result with the degree discount heuristic, which is shown below, and the heuristic that simply choose the max degree. And we observe a similar scenario for the weighted independent cascade model. But for the uniform independent cascade model, our algorithm is not that, is slightly worse because the theoretical upper bound doesn't work for the uniform independent cascade model. So I'm going to skip the conclusion since I do not have sufficient time. And for the future work, one apparent future work is to further close the gap between -1 and 1 minus tau. And another line of work is try to extend Khanna and Lucier's 1 minus 1 plus C approximation result to the linear threshold model as well. I mean, undirected linear threshold model. Yeah, that's all. Thank you. And by the way, the video presentation of this long version of the talk is available on YouTube. You can just search for the title of this paper on YouTube and you will find it. Thank you.
Are there questions? So are there ideas on the directed version of this? How this can be done?
On the direct version of this APX hardness result, yeah, if it's hard for undirected graph, the more general directed graph is also hard. I mean, the hardness result just extend, but for the positive result, I think for the directed case, both linear threshold and independent cascade model, the greedy can at most do 1 minus 1 over E.
All right. Any other questions? Okay. Thank you again.
Thank you.